but we are going to go ahead and get started. So let's talk about where we are. So last week we got introduced to vector fields and line integrals. And now we're looking at ways of calculating line integrals. So today we're going to talk about something called the fundamental theorem of line integrals. You guys have gone through the video lessons, so you already have an idea. And to be honest, when we're able to apply this, it is one of the easiest ways to calculate a line integral. It's just that we're not always able to apply it. So what I'm going to talk today about is a little bit about, just give you an idea of why this theorem makes sense. And then we're going to look at specifically when we can apply it. All right. So we're going to start off by talking about gradient fields. We've talked about this a little bit before. All gradient fields are vector fields, but not all vector fields are gradient fields. A gradient field is a specific kind of vector field. And specifically, it's one where the vector field is the gradient for some function f. We call that function a potential function. So you'll hear me use that term every once in a while. Hey, can we find a potential function? Or this is the potential function. What we're doing there is we're basically working in the reverse of what we did in the first half of the semester. In the first half of the semester, we were given a function, and we would find the gradient. Now, if we have a gradient field, we basically have the gradient, and so we might go back and try and find the potential function. All right. The reason we like this is because if we have this potential function, if we want to find the total change between 2 points in a plane, we could use the function evaluated at those 2 points and find the difference between them. That would give us the net change. It's very similar to our fundamental theorem of calculus, hence its name. Now, the alternative way of approaching this is if we had a curve C going some path, going from P to Q, we could break it up into small pieces, estimate the change on each piece. What we would do in that case is do the rate of change of f times the distance moved in the direction C on each piece. That is essentially our line integral that we were talking about last time. So basically, what this is going to do is give us an alternative way of doing a line integral when our vector field is a gradient field. Okay? So this is what the fundamental theorem of calculus for line integrals says. If we have a piecewise oriented curve starting at P and ending at Q, it doesn't matter the route. And f is a function whose gradient is continuous on the path of C. Then our line integral can be calculated using the fundamental theorem, which basically says we just evaluate our potential function at each of our points. Now remember that little f is our potential function for our gradient. This is going to be really advantageous to us because what this says is if our vector field is a gradient field, then all we have to do to calculate the line integral is find our potential function and evaluate it at our 2 points. And you can see how the process is really analogous to our fundamental theorem of calculus from back in Calc 1. Now I'm going to talk a little bit about the properties, and then we're going to do one of these here. We'll actually do the example that we did last class, but something I want to talk about first is what does it mean when we have a gradient field? Okay. So first off, if Q equals P, in other words, we're going back to the same point we started at. So we started at P and we end up at that's both point P and Q. We have what's called a closed path. And the integral will be 0 because if P equals Q and we're doing f of P minus f of Q, sorry, not theta, these, if P is equal to Q, those are going to be the same. So we get a 0 for our line integral. That's regardless of the path. Okay. When this happens, it is called path independent because, again, it doesn't matter how you get from P to Q. So this is just more in general, not necessarily a closed path, but regardless of whether I go this route, or even some funky route here, the line integral will be the same if our vector field is a gradient field, and they're called path independent vector fields or conservative vector fields, because the integral only depends on the endpoints. So we call those conservative vector fields. Also path independent vector fields. All those two terms are synonymous, or we could call it a gradient field. All three of those things are telling us the same thing. Tells us it doesn't matter what path we take to get from one point to another, our line integral is going to come out the same. Now, to do the fundamental theorem, it is going to require that we find the potential function. So we're going to talk about that in a couple slides. There's a couple things I want to mention first, because obviously, if we have a path-independent vector field or a conservative vector field, we're very happy about that, right? Because we no longer care about the path to get from between the 2 points. We only care about the potential function. So let's talk about how we identify that. Well, let's say C is a simple closed curve. In other words, it does not intersect itself. So, our drawing over here would be an example of a simple closed curve. And we let P and Q be 2 points on the curve. So in this case, they're not going to be the same point. So let's not let P equal to Q. Let's change that. So maybe point P is up here, and we'll put another point Q here. And C1 is one of the paths, and C2 is the other. So maybe C1 is going along this way from P to Q, and C2 is going from Q to P. Well, then we know that those two are equal because we have a path-independent vector field. So what happens is we can essentially say, all right, I'm going to look at the path from C1 to the opposite path on C2. Then from our property of integrals, that's the same as the negative of the integral on path C2, which equals 0. Basically, what this is saying is any two paths that we take from P to Q are always going to subtract to 0, because this thing is path independent and the path does not matter. Now, what does that mean for us, right? Like, we're not going to be able to test every path from P to Q to see if it's path independent. So this is not an efficient way for us to determine that. So let's talk about how we figure out whether what we have is path independent or not. So it's path independent if and only if the line integral is 0 for every single closed curve C. Again, we can't make every possible closed curve in a vector field. So we're going to look at something that you guys saw in the video lessons. So what we're going to do is to see if a vector field is path dependent. What we look for is a closed path with a non-zero integral. Now, we're going to look at doing this algebraically and basically see if we can find potential functions. So one way of going about this is to take our vector field. Now, what would this be saying if it has a potential function? This is saying that f sub x equals 2xy and f sub y equals xy. So if we were looking for a possible potential function, we look at possibilities from both partials. So we would take the antiderivative with respect to x, which would be x squared y, plus it could have some constant in terms of y, so we'll call that c of y, plus it could have some just general constant. Excuse me. All right, we do the same thing here. We take the antiderivative with respect to y. So that would be x y squared over 2. Taking the antiderivative of y, remember x is a constant. Now there could be a term that is only in terms of x, and then there could be some constant. Now, when we have a term in terms of x and y, like we do here, we call those interactive terms. If there is a potential function, those interactive terms must be the same. Because we have xy squared over 2 here and x squared y here, this term and this term, there's no way we're going to be able to find a potential function for both of these. So that tells us that what we have is not a gradient field, and therefore this is a path-dependent vector field. Now, that's all well and good, but it can take a lot of time to go through this process of doing the antiderivatives. So what we do is we actually use another way of testing. So let's talk about this. So we have some vector field, and if it is a gradient field, then we know that f1 is the partial of f with respect to x, f2 is the partial with respect to y. So we can leverage this and what we know about partial derivatives. If you remember back to the first half of class, our mixed ordered partials come out equal. So if we took the derivative of excuse me, if we took the derivative of f2, if we take the derivative of f1 with respect to y, and the derivative of f2 with respect to x, we're looking at the mixed order partials. Now, what does that mean? Let's go back to our example here. Well, that means I would want to look at f of xy, which in this case would be 2x, and I would look at f of yx, which is going to be x. Excuse me, not x, it's going to be y. These two are not equal, therefore our mixed partials are not equal, so there's no potential function. Now, I want to match this up with this notation here. This would be f1. This would be f2 from the notation on the slide. And then what we're doing is we're doing the derivative of f1 with respect to y, that's what's making it a mixed partial, and the derivative of f2 with respect to x. Okay? Those are the mixed partials. Now, we are going to actually combine this with something we did last week, and this is what you saw in the videos. Because when we're finding df2 dx and df1 dy, we're finding the components of the curl. So one way of testing it is by doing the curl, and if the curl is 0, we know that we have a path-independent vector field, and therefore there is a potential function. All right? So this is what's called the curl test. And we were practicing doing curls last week. So we're actually now using the curl to figure out whether or not our vector field is path independent or not. So whenever you have a curl that is 0, well, there's one thing we're going to have to add, and I'll add it here in the next slide. But we're going to be looking at the curl, and when the curl is 0, we have a path independent vector field, provided one thing, and we'll look at that here next. But the curl we've got practice finding. It's not difficult. And once we know the curl is 0, then we'll go through the process of actually finding a potential function. If the curl is not 0, there's no work for us to do as far as finding a potential function. It's not a gradient field, and therefore is not path independent. Guys, and as I'm going through this, if you have any questions, let me know. We're going to do some examples to help make this a little more concrete. So we actually did this up here. We just didn't do it formally. So what we would do is we would take our vector field, which was 2xy, comma xy, and we would calculate the curl, which is the derivative of xy with respect to x minus the derivative of 2xy with respect to y. That's our curl. It does not come out to be 0, so we know that we have a path dependent vector field. All right, that's how the curl test works. Now, here's the formal definition of the curl test, because there's going to be one thing that we're going to need to attend to, which will happen on occasion. So we have a vector field, and the domain has the property that every closed curve in it encircles a region that lies entirely within its domain. It has no holes. So we're going to do one case where it works out perfectly, and then we're going to look at a case where a hole becomes an issue, and we'll see what happens. And if our curl comes out to be 0, then we know our f is path independent. Therefore, it is a gradient field, and it has a potential function. Now, this was our example from last class, okay? And we did it via parameterization. We got this messy integrand, which, as we discussed, would need to be split into 2 integrals, each done with integration by parts. And we saw that we calculated the answer in Symbolab. Let us run it through the curl test. So our vector field is negative y sine x cosine x. Right, so that's our F1, that's our F2. So just as a reminder, and guys, this isn't a formula you have to memorize. This is something that can go on the note card, so don't worry about that. So to calculate the curl is df2 dx minus df1 dy. So the derivative of f2 with respect to x is the derivative of cosine, which is negative sine x. The derivative of f1 with respect to y, sine x is now a constant. The derivative of y is 1. It's negative sine x. So negative sine x, basically plus sine x equals 0. This is a conservative vector field, or this is path independent. That's good news, because that means there's a potential function. So let's talk about finding a potential function. F sub x is negative y sine x. F sub y is cosine x. So taking the antiderivative of this with respect to x, remember y is a constant. The antiderivative of negative sine x is cosine x. So a possible potential function here is y cosine x plus a possible constant in terms of y, because that would be 0, taking the partial with respect to x, plus a possible constant. Here, cosine of x is a constant with respect to y, so taking an antiderivative with respect to y would yield y cosine of x. There could be a constant in terms of x and some general constant. Well, look at what happened here. Our interactive term came out exactly the same. We have no need for a constant in terms of y or a general constant. So we have a potential function in this case, which is y cosine of x, which means we can apply the fundamental theorem of line integrals. So our f dot dr is going to be y cosine of x evaluated at our 2 points, 2, 4, and 0, 0. So y is 4, so we're going to have 4 cosine of 2 minus, now our other point is 0, 0, so 0 cosine of 0. That ends up just zeroing out. And there's our 4 cosine of 2, which is what comes out to be that negative 1.66458. Now, I think you guys will agree that doing the line integral this way was simpler than having to do each of these with integration by parts. So again, anytime we have a path-independent vector field, we want to find that potential function because it makes the line integral very easy to do. Questions about this example?
Question.
Yeah.
In the part where you do the partial of f with respect to x, yeah, right there. So
Right
that's
here?
the partial of x. No, so on the lower, like, yeah. So that's the partial of the x component of the vector with respect to x?
So it is the x component of the vector.
Oh, okay.
So yeah, let's do this. So that is F1.
Okay, I got you.
And that is F2. No, that's a good question. It's a good clarifying question.
Yeah, I thought it was a partial with respect. So up there, though, is up so right below that curl. The curl is the partial.
Yes. So here's what's going on. If our vector field is a gradient field, then it's already made up of the first order partials of the potential function. Then when we're doing the curl, it's actually the second order mixed partials of the potential function, even though it's only the first order partials of the vector field. Did that make sense?
Sorry, can you repeat that one more time?
Okay, I don't want to make, hopefully I'm not making it worse. All right, so let's kind of look at the order here. So if we have a potential function.
You can just repeat it. Like my cat was sticking its arm under my door.
Okay. I can't say I'll be able to repeat it verbatim, but.
Oh, okay. All right. I'll explain it however you want to. Yeah.
Yeah, but you guys let me know because there's two things going on here. So if our vector field is a gradient field, then it's made up of the partials, the first order partials of the potential function. When we do the curl test, we're finding first order partials of the vector field, but those are already first order partials of the potential function. So when we're doing the curl, we're doing the mixed partials of the potential function.
Got it. So if there's 0, that's why that matters.
Yes.
Okay. And then, okay, so then F1, F2, we just integrate them, and if they have, and then we put their parts together essentially, especially if they have the same parts, then we know that we put them together.
Correct.
Okay. Thank you for answering that.
Yeah, oh, no problem.
That f, the lowercase f sub x looks like, partial with respect to x. Yeah.
Yeah. And it is supposed to, like, that's supposed, because that is the partial of this function with respect to x. And this is the f sub y of this function with respect to y. But then when we're doing the curl test, we're actually taking the partials of f1 and f2, which are the mixed partials of the potential function. So, so when we're doing the curl, they're first order partials of the vector field, but they're second order partials of the potential function. So hopefully that layering makes sense, because it's an important clarifying point on this of what we're looking at. Other questions at this point? Okay. I want to do, okay, we did the curl test. All right, so we're going to take a look at this one. I am going to go through it a little bit quickly, just for time's sake, but it is worth looking at. So we have the vector field negative y over x squared plus y squared, and x over x squared plus y squared. So that's our f1 and that's our f2. So when we do the mixed order partials, so I'm not gonna go through all the steps on this because there's actually something I want you to see. So when we do df2 dx, what you get is y squared minus x squared over x squared plus y squared. And then if you do df1 dx, it's very similar, but you get, actually you get you get x squared.
Wait, should one of those be y? With respect to y, or are they both with respect to x?
Oh, sorry, thanks. That should be dy. You actually, so again, without going through all the steps, you actually get the same. Let me fix that. So the mixed order partials are actually equal. You'll get the same. So y squared minus x squared over x squared plus y squared. So when we do the curl test, the curl of f is going to equal 0 because our mixed partials come out the same. Now what we're going to do is we're going to look at what happens on the closed path of C, which is the unit circle centered at the origin and oriented counterclockwise. I'm picking that for a very specific reason. It's easy to parameterize. X of t is cosine t. Y of t is sine t. And t is going to go from 0 to 2 pi. Okay, that's straight out of trig. That's our circle. Now I'm going to actually do this line integral of this vector field along this path parametrically. So the way we were doing them last week. So I do need, x prime of t, y prime of t. So this will be a little bit of review. So sine of t dt and cosine of t dt. So all I'm doing is taking the derivative of our parameterization. And so just as a reminder, we're doing the line integral of f dot dr, which in this case is going to be our vector field using our parameterization. So what's that going to look like? Well, we're going to have a negative y, so a negative sine t over cosine squared t plus sine squared t. Oops. Don't really need that parenthesis there. All right, so what I'm doing is I'm putting in our vector field, but I'm substituting in our parameterization. And again, I'm going through this one a little bit quicker because I just don't want to take up too much time with it. There's just one thing I want you to see. And that gets dotted with our dr, which is negative sine t cosine t dt. Now, one important thing to point out here, this is a closed path. We got a curl of 0, which normally means path-independent vector field. Any closed path in a path-independent vector field should be 0, because that means we're starting where we're ending, and by the fundamental theorem, we would get 0. Something interesting happens here, and we'll talk about why here in a second. Now, we know cosine squared plus sine squared actually just ends up being 1. So those denominators work out real nice. Now we do our dot product. So negative sine times negative sine is a positive sine squared t. Cosine times cosine is cosine squared t dt. Once again, this is 1. So we just end up with the integral from 0 to 2 pi dt, which is 2 pi. If this was a path-independent vector field, that should have come out to be 0. All it takes is one non-zero closed path to say that it's not path-independent. This isn't a path-dependent vector field. Well, here's why. Notice that x squared plus y squared, that is 0 when x and y equal 0. So this actually has a hole at the origin. What that does, when we have a vector field that has a hole in any of the paths that we're looking at, and in this case, it's right in the middle of our circle here, we lose that guarantee of the curl test. So if I go back, has the property, it has no holes. Okay. That is something we need to be aware of. It's not something you're going to see a lot in this course because we're going to be dealing with vector fields that don't have holes in them. But I just wanted you to be aware that we lose the guarantee that having the curl equals 0 means it's path independent. And so we might not be able to use the fundamental theorem of calculus for line integrals on vector fields that have holes in them. We have to go back and use parameterization. All right. So it's a bit tricky, but again, when it happens, it's really obvious. You'll get 0, you'll get a massive hole in your vector field, and it'll happen when you have zeros in your denominators. All right, so it is one thing we do need to be aware of. It is a breakdown in that theorem because the condition of the theorem is not met. Again, most of the ones we're going to work on in here, that's going to be a non-issue because we're specifically practicing to use the fundamental theorem, but I want you to be aware of it. All right. We do have a vector field, a curl test for vector fields in 3 space, and it works the same. So if the 3D curl is 0. Now, if you remember from last week, we did 2D curl and 3D curl. The 2D curl is a scalar. The 3D curl is a vector. It has to be the 0 vector. In other words, all 3 components must be 0 in order to say that we have a path-independent vector field. All right. If it is, once again, there's no holes, then we can say F is path independent, it is a gradient field, and it has a potential function. So we're already starting to see why we were calculating those curls last week, because they can specifically tell us if we have a conservative or non-conservative vector field. And we've now seen the advantage of having a conservative vector field. It makes line integrals much easier to calculate because all we have to do is find a potential function. Questions at this point? Then I think at this point, I'm going to have you guys try some, because this is not a bad section. The things I want to get you the opportunity to practice are, you know, finding a gradient field. That's something we've done before. Using the curl test to determine if we have a path independent vector field. And if we do, find a potential function and use that potential function to find the line integral. So let's see. All right, sorry, I dropped something over here. Okay. Give me 1 second, guys. Sorry. Something got misplaced. Let's see, we have, okay. Okay. Sorry, I got to make one slight adjustment to this. We don't quite have enough people for 3 groups, so. Okay. So there's going to be the problems. I'll put those in. I'll send those out to you once you guys are in groups. If you guys have any questions, I want you to go ahead and try one of each problem on this worksheet. And, you know, once you're in groups, if you have questions, just let me know.